Okay, so HSM is used to observe crystallization process, dissolution, polymorphism, phase transitions, melting point, boiling point, glass transitions, and several other parameters for the sample. So this is what basically hot stage microscopy goes around. And if I talk about setup, so hot stage microscopy, you will have an optical microscope, and then you will have an heating cooling stage with a window where a microscope can observe the sample. So we'll point by point go towards the setup now. So advanced hot stage microscopy setup. So point one, so probably here we are talking about this stage, this software control hot stage with temperature ramping facility. So ramping facility means you can increase reach to a temperature, stay there for a time, and then go to the next temperature. Maybe you are going to 100 degrees Celsius, staying there for 10 minutes, so that that entire sample reaches 100 degrees Celsius, because there is a glass slide, there are liquids, there are cover slips, so that all of that are homogeneously in the same temperature. And then you go towards maybe 50 degrees Celsius, you increase the temperature further, stay there for X minutes, 5-10 minutes again, and then you ramp. So sometimes if there are phase transitions which are happening and maybe in a slow rate, may be missed if you're not going with ramping. You may see some transitions happening at 99 and other happening at 120. Probably they're happening at 100 only. So ramping is very important, allowing and then allowing control heating and cooling as per rate defined. So you define the target temperature, maybe you're going to 100 degrees Celsius or 300 degrees Celsius, and you also define the rate at which you want it to go, maybe 5 degrees Celsius per minute, 10 degrees Celsius per minute. So hot stage should allow that. Then an optical microscope with the reflected light and transmitted light. So this is a microscope, point number 2 and 3. So this is a Olympus DSX 1000 microscope, which has a reflected as well as transmitted light facility. It has basically 5 observation methods, but normal microscope or any microscope should have minimum 3: bright field, dark field, and polarized light. So bright field is a observation in transmitted or in reflected. Light falls in a conical form on a sample. You see the color of sample is a data for you. And then dark field, background goes black and you can see crystals and fine particles glowing in the background, dark background. So it's very easily, it becomes easy for find the particle. And third one, polarized observation is very important, because here we are able to understand the particle if it's in crystalline form or in amorphous form. So crystalline particle will have bonded chains, so they will start giving birefringence pattern, and which is a very useful data when we want to understand whether a particle after melting or in a cooling, in whatever phase it is it crystalline or in amorphous form. So this is point number 2. We're talking about microscope. Then third is image capturing facility, high frame rate. This is should be there to capture image and also should capture the video, and with temperature stamping, date stamping, time, and micron marker stamping for the measurement. So this is very important when we are wanted to do the analysis. We have captured the image at ambient temperature, and we have captured the image after 100 degrees Celsius or 150 degrees Celsius. To know the particle size as temperature changes, micron marker becomes the data with which we can calibrate the image. Then fourth point, the sample is heated on a glass slide with cover slip or without cover slip with compatible liquid. So it depends whether we are observing sample in an open environment as it is, you are placing particles on a sample, or you are dipping it in liquid. So if you are putting in a liquid like glycerine have got a boiling point of roughly 290 degrees Celsius, and if my particle melting is 150 or 200, probably I can use glycerine so that my liquid is covering entire sample, entire 360 degree of the sample, and gives him the homogeneous heating. Of course, we need to also understand whether our sample is compatible to glycerin or it changes the form. So once that is studied, so you can also use relevant liquid cover slips if fumes are there. So this is the way how we can place the sample. Then hot stage should also allow controlled cooling and gas purge in chamber to allow experiment in various environmental conditions. So it is very important so that you have a gas purge, because when you're doing controlled cooling, condensation is being taken care by the gas purging. Normally argon or nitrogen gas is used to purge, because these are dry gas. And then it also helps you to create different environmental condition to remove oxygen from the chamber. You can also have an environment created from an external gas. So this fifth, if you can see this arrow, this is are the gas purge points. Then hexagon hot stage have various models to give temperature range from -40 to 600 degrees Celsius. So depending on the different model, you can choose the model which suits your application, whether you're working into below ambient or below zero, or your samples you want to study about 200-300 degrees Celsius, depending on that. It's a small video on how we are placing the sample on the hot stage. So now I'll be target temperature 310 degrees Celsius. Then you put a hold time and then rise rate. So you can see T mapping over here. Over here you can have multiple maps possible. You can have 10-15 maps. So now you can see that this graph will try to show you the temperature change. It's just like this. So this is how quickly you can place the sample on the hot stage. This is how we place a sample. Sometimes you may have liquid or without liquid. So let's start with the application of HSM in pharmaceutical. Specifically, we'll start with the morphology study. So morphology word itself talks about the physical dimensions of a sample. It can be size, shape. Then you have got, maybe you're looking for inner diameter or rod shaped particle to differentiate them. And it is also important particle when we're trying to understand the distribution of particle and change in shape.
Your voice is not clear, huh? Are you mute?
Is it okay now?
Okay.
Yes, thank you very much. If there is anyone, just let us know. It will help us. Yeah. Thank you very much, sir. Okay. Okay. So yeah. So uh, study API changing shape while heating and regenerating as amorphous or crystalline while cooling. Then we understand the melting point of API and excipients, which is also part of morphology study. And then real-time visual observation helps understand small changes in surface which may be missed by DSC and TGA. So this is one of a sample. This is one of a sample. Just hold on. So this is one of our tablet sample. It has excipients, API, which is in white, and you have this red. These basically are the polymer. So at 35 degrees Celsius, you can see this sample air room looks like a normal one. But as you increase the temperature at 160 degrees Celsius, you can see that there are some particles shining. These are birefringence pattern, and then an excipient which is melting. So this is an API and a melt. So this is happening at 160, and slowly you can see in the bottom part where this polymer have also started melting. So you can just understand the morphology, what temperature, melting point, and shape change of a particle. Then this is the same crystal which we have shown you the video. This is the same crystal. You can see at 35 degrees Celsius, we now see the shape of a particle clearly. It's a cuboidal shape. Some are some have got are quite bigger in size, some are smaller. And then at 300 degrees Celsius, you can see them. They have started melting, and at 308, you can see they are into flake form, and also you can see they have a capability of glowing capability. And so the melting point roughly is 308 for this. How they are melting, we can understand from that. So this is part of a morphology study which we have done. Now, this is basically a 40 minutes video. Of course, we won't play all of them, but 2, 3 points we'll be talking very specifically. First is just see this entire image. On the top, we have got date stamp, time stamp, and a temperature stamp. And bottom, we have got a micron marker. Now, this is a sort of an API sample. Now, I'm gonna play the video. Just to watch this, and you can see some small movements here. So once I'm playing the video, there are very small transitions happening while the video is played, which may not be seen by us very easily. Here we have recorded entire video of 40 minutes. So it has its own benefit to see those changes. So let me just try to bring your attention to a specific region. Just watch this region. So till now, I can say, okay, I'm not able to see details very clearly. Okay, some changes are happening, but yes. Now just watch. I'm trying to bring back and I'll just scroll down through it. Just watch on this red region, and you can see this. I'm changing, and you can see those changes happening in that region. So these are the excipients which are melting. So first form, you can see that there was melting happening, but which was not seen. It almost took us 15 minutes time to understand that change. Now you can see these bigger particles, they will also start melting at a specific phase. Like it has started. Can you see this one over here? Second melting. And see the top temperature is 153.6. And now I'll be showing you now this rod shape have their own melting, something like this. So you can see them, individuals are melting. So this changes is seen easily, but a lot of changes are not seen that easily. So a video file will every time help you to come back and see just like this, I'm doing the observation. You can just go ahead and go back and see the transitions again. So normally in hot stage microscopy, people used to capture the image to see those details. But if you wanted to, if you have a video, probably you can recheck those regions again and capture the image for that specific temperature region. So this is how entire temperature affect the sample, not only in the size and shape, but also the morphology. And in polarized light, we can also understand the crystalline form. You can see that there are gray crystals here. These are the gray crystals. In the birefringence pattern, gray and yellow is also a first order band. So this also talks about crystal structure of this API sample. So this is a quick, of course, quite big video. So this is how a sample melting helps you to understand different morphological change in the sample, not only for a specific API, but also if it's a mix of big multiple regions. So we have seen some samples change their shape first in a rod shape, and then at a specific temperature they melted. So these are the possibilities with hot stage microscopy. Now let me go ahead and now will be next topic is amorphous and crystalline form characterization. So this is an image which is basically crystal. You can easily see a birefringence pattern. So this sample was heated, is an API sample, and when we cooled it, it formed a rod shape, and we can see a color birefringence pattern. Same way here also and here also. So the amorphous form of API is preferred in the pharmaceutical industry due to their higher solubility and dissolution rate over crystalline forms. With a hot stage microscopy fitted with a polarizing filter, amorphous and crystalline forms are easily distinguishable from one another. So crystalline materials are known to show birefringence pattern. This is what we were talking. While amorphous material lack birefringence pattern, hence that can be easily distinguished when we use hot stage microscopy. So HSM is a great tool to study the conversion of an amorphous API to crystalline form under the effect of heating. So HSM is useful for researching crystal growth rate as well as the effect of storage, particularly when it comes to heat and humidity. So if you can see this sample at 35, we can see the birefringence pattern, and at 70, we can see the softening point of it, and at 73, you can see that entire sample is liquefied. So after this point, if we cool it, whether they will crystallize it, if they crystallize it, is it going to have a same form or they won't crystallize it. So this is where we understand amorphous and crystalline form of a sample. Same way here, if you see, this is an API sample, and at 10 degrees Celsius, you can see one of a region have crystallized, but others are not. But at 5 degrees Celsius, you can see that this region has also formed rod-shaped crystals, and also they have got a color pattern, which means API sample, if this API sample is there, and if you are trying to preserve it, if it gets exposed to environment where temperature is 5 or 10 degrees Celsius, so this will be the challenge with this API. So one has to, one can understand the scenario and can make changes, use a relevant solvent. So this will be the part of study. So API recrystallizing while cooling cycles. And sometimes some API, some excipients may have multiple heating, cooling, and they change their form. So it is not that if once it is not changing the form, probably after 20 or 30 cycles, I can understand the change in form. So even that part can be studied as a pilot project on the hot stage. Uh, Polymorphism. So polymorphism is the ability of substances to exhibit more than one crystalline structure. So different crystalline structure are produced when structural molecules are arranged differently, a phenomenon known as polymorphism. The physiochemical properties of an API can vary among its different polymorphs. So polymorphism can also be induced by drug manufacturing process also, like drying, milling, recrystallization, storage. So polymorphism cannot be produced in a laboratory because of thermodynamic energy factors, but they can be produced and studies on a hot stage because you can actually simulate that entire environment. Maybe if it's transporting towards a heated region or a humid region, or it is transported into a hilly area where you can understand where there are icing factors are there. Then HSM may be used to differentiate between polymorphs having a small difference in melting points. I think this we have just now seen there was a difference in melting point for two excipients, which was very sharp, as well as to check the stability of a polymorph at a given temperature. So in polymorphism, there are several papers talking about this. Couple of them I have selected here. Of course, this is a reference on the bottom. So at 175 degrees Celsius, the melting of form 3 was observed in HSM. HSM here I'm referring to hot stage microscopy, which was missed by DSE. So if you can see in this image, 100 degrees Celsius, this region is an interest of observation. And at 149, you can see that this region have become transparent. That crystal have started showing transparency. But at 175, the particle which we are not seeing is over here, region 1, 2. These have started melting. And then region 3 is again the particle of our interest. So this particle, which started melting at 175, was not observed in DSE. If you can see the DSE data, there is no heat flow over here. So this is missed by DSE, while in hot stage microscopy, we can easily see here that this has melted. Of course, if you have a video, we can run the video. We can have a back and forth reading of the video so that we can understand, or we can specifically focus to a specific region to understand the effect of heat and different transition temperature, which may be missed by DSE and TGA. DSE specifically. So these are DSE curve and HSM light intensity of sulfathiazole crystal obtained by method 4. Then, of course, there are several other papers for this. If you wanted, I can share you more papers on this. Co-crystallines. Yeah, you have to join someone. So co-crystallines. So co-crystals is a multi-component solid consisting of two or more different molecules, non-covalently bonded within the same crystalline structure. So co-crystals have recently attracted significant scientific attention due to their ability to modulate the physiochemical property of API. So screening through HSM, it's a rapid method and solvent-free and requires a very small quantity of API to study that. So one of an example of co-crystalline material is on the screen. Let me just show you. So on the top, of course, temperature is not seen that clearly. It's like 85 degrees Celsius, and you can see. Just focus on this region. So now you will be able to observe that while one of a particle is melting, other is not. This is because also the thickness of that specific particle. So you can see slowly it will start becoming yellow. If I can show them this region, and then it will change its forms. You can see it is changing its form, and then again it will melt. So this way, so multiple melting points for same sample, and also you can see because of the thickness of sample, one sample melted but others not. So even thickness, the bottom side have started melting. So sometimes we use liquid so that entire 360-degree of a sample is under a liquid, and liquid will help him to homogenize the temperature across the sample. Second part is, so basically we are talking about all these variants of a sample in the pharmaceutical industry. So you can see samples are amorphous in the form, they are polymorphs, they are salts, polymer solid dispersions, then solvents, hydrates, and then pharmaceutically acceptable molecular co-former. Then you have got ionic bonds. So these are the things which we are actually discussing, and this is where our topic we are trying to get all the points. This is one more example of a co-crystal screening of API with glutaric acid. So glutaric acid was chosen as a potential conformer based on melt experiments because it's good aqueous solubility and melting points. So I would like to focus on few regions. So this region is an API region, and this is your glutaric acid region, and this is a eutectory channel. So every change will happen here only. So you can see in the first image, API is forming, and in B you can see API have formed a quite good region, and then it is increasing. So you can see over it written also. So okay, yeah. So HSM micrographs of co-crystalline screening of API with glutaric acid. The upper half of the micrograph shows the API, whereas the lower half is glutaric acid. So this line differentiates, this curve differentiates, and then in the D, if you see, this glutaric acid side will start melting while API have already crystallized over here, already over here, and this glutaric acid will start melting. You can see it has already melted over in E, and then it regenerates, it recrystallizes at F. So E, melting of glutaric acid, F, recrystallization of glutaric acid. So you can see the flakes also over here, glutaric acid flakes. And now this is a eutectic region. So this is what co-crystal screening is. Of course, you can continue with the reading. This is a paper from Kumar A. Singh. I can also share you this paper. So this is a great example of co-crystalline screening. So now our fifth point is, any questions, you can of course drop me the question. Is there any message question? Yeah, I'll answer. So Bhakti, I'll answer that point. That is specific to a model. I'll share you the brochure of that and answer that also. So I was asking question, if there is specific question on the application part, you can pin me. So now fifth part is particle size distribution and characterization of API in tablet. So there are several instruments used in pharma industry for understanding the particle size of the sample from the, because we use raw material and then we bring down the size. So particle size distribution is an important part of drug development, and particle size distribution has a significant impact on the processability of raw materials and finished products. So particle size distribution influences dissolution, bioavailability, and stability profiles to ensure quality, safety, and efficiency of the finished formulation. So method exists to determine the particle size in tablet, but they have their own limitations, including inability to distinguish between aggregates of the tablet and ingredients. So here we are trying to study the particle size with a change in temperature. So if you see at 30 degrees Celsius, this is how the sample is. Of course, there are agglomerates, but here we are trying to understand how temperature affects different excipients. So this is at 172. You can see that all this API and other have melted, but some of the excipients have not melted. And at 206, excipients have started melting. But at 240, you can see not all excipients have melted 100%. There are forms which are turning into brown, which means now those excipients have started becoming they are becoming start becoming charring effect is started, and they are becoming brown. So this is how we can understand whether there is a particle size distribution at every temperature range, or we are trying to understand the temperature at which entire sample or entire excipient dissolve, or we are understanding the particle size at any point of time of a sample. Of course, it can be oriented to a specific region of interest, or it can be for entire sample. Then sixth point is solvates and hydrate screening. So now in the earlier slide, you must have understood about the solvates. So when you have got molecular drug substance combined, uh, maybe in any process of manufacturing, if they are combined with water, they create their own channel, and then they create an isolated site. So this is very common while we are formulating, where we are processing. So solvates are unavoidable compounds formed during various pharmaceutical processes such as crystallization. Solvates are formed when solvent molecule are incorporated into the structure of a host compound. When water is incorporated into the host compound, these solvates are called as hydrates. Hot stage microscopy can also be used for solvent hydrate screening, as it allows visual observation of the gases generated during sample dissolution under heating. So such samples, if we expose, and we can understand the change, and we can see those gases coming out. So here hot stage microscopy again becomes a important screening tool. So sample size will be very small, and we can also use different sensors inside the chamber to check whether those gas emitted, we can study those emission of gases. Then pharmaceutical incompatibility and miscibility. The problem of pharmaceutical incompatibility is well known in the pharmaceutical sector. To determine the effect of incompatibilities on the stability of pharmaceutical formulation, it is necessary to perform a rapid and real-time storage studies under real or harsh conditions, which is time-consuming and expensive. So therefore, pharmaceutical industry still feels the need for alternative techniques for rapid and economical incompatibility detection. So we already know that DSC has successfully used to detect compatibilities of binary mixtures, drugs and excipients. So additionally, using the visualization capabilities of HSM in this regard have proven beneficial because interactions can be observed visually, which is limited in DSC studies. Therefore, HSM can be used to supplement data obtained from the DSC to detect compatibility or incompatibility. So this is what a general term of pharmaceutical incompatibility and miscibility talks. Then one of again same paper we have discussed where there's a two there's a temperature change study of chromic acid and quinine solvent at different temperature. So like 24, this is at 73, 99 degrees Celsius. You have got this 152, and you can see as temperature changes, you can be able to see the bubbles. Basically, these bubbles are the evidence of contact layer between the two specific components, and so this helps us understand the compatibility. So it can be any two substances which can be used to study the compatibility, and hot stage microscopy becomes an easy tool where we can have a small sample and run off a pilot samples and understand the incompatibility. So the appearance of bubbles signifies the release of solvent molecule. So that's what it is. So this is what the material is melting at specific temperature. Then thermal analysis by surface characterization. This is an advanced technique, and so thermal analysis by structural characterization (TAC). This is what the term you will be hearing, TASC. So it's a new thermal analysis technique that includes hot stage microscopy and image analysis software. So as a thermal experiment progresses, a series of images are created. So normally you capture entire video. In Hexon we capture entire video, and also we are able to extract images, which is per degree Celsius change, or maybe it can be per second or per frame rate wise. So these images form the basis of TSC. So there is an TSC is basically an algorithm which focuses on the region of interest. So the TSC algorithm works by scanning a region of interest that covers an area on the surface of the internal sample, which is called as target area. So you define a target area and the area around the sample that the sample can move during heating. So while sample is heated, you may observe that sample is reducing in size or increasing in size. So you can study the change in that. So image analysis software will analyze these images to detect changes in the sample surface by scanning the image and subtracting the ROI of the first image. It's just like, so this is also a reference, a standard paper studied. So this is an article I thought to include. So you can see this first image, entire particle is there, and you can see this image. So every image will be compared from the first image. So this is the first image, second, third, fourth, fifth. So it compares every image and creates a graph like this. So TSC can provide so image analysis software will analyze these images to detect the changes in the sample surface by scanning the image and subtracting the ROI of the first image from the corresponding ROI of the subsequent image and creating a curve. So TSC can provide information on melting temperature, transition temperature, heterogeneity, dissolution behavior, and glass transitions also. So this is very important and quite advanced tool now. So you can create your own region of interest and then focus on a specific particle and then take those images which will be run by the software, and you get a TAC curve. So of course you can have further reading from this article. I'll be sharing with the paper if you want. So I think we have covered our 7 topics of introduction. Of course, there is a time constraint, so we try to give you few examples and what term means. So just to conclude, these are the applications which we covered was amorphous crystalline form characterization, polymorphism, co-crystalline staining, particle size distribution and characterization of an API in tablet, then solvate hydrate screening, miscibility, thermal analysis by surface characterization TSC. So on conclusion, so hot stage microscopy has become a popular and routine technique in pharmaceutical characterization. So it is quite rapid to understand the solid state property of various pharmaceutical compounds. So HSM has its own advantages because you are able to visually see the change in sample, which normally is missed by conventional technique. And so additionally, HSM is also a tool which can combine with DSC, FTIR, Raman, PXRD, SEM to benefit from the simultaneous benefits of both techniques. So we can understand the change in temperature visually, as well as we can understand the other parameters, which will be quite helpful in research fields. And so in order to gain a thorough understanding of the solid state properties and subsequently increase control over pharmaceutical formulations, HSM has the potential to be used as standalone technique in pharmaceutical analysis, as well as complement the findings of other thermal characterization techniques like DSC and TGS and other techniques.